Hi, I'm Dalton, and this is my presentation over Physics 2212's Lab 5. So here's a quick little introduction. The main purpose of this lab is to observe the motion of a falling magnet through an aluminum foil tube and model the scenario using a computational model. So for this experiment, our system and surroundings are going to be as follows. The system having the bar magnet and the aluminum tube, and the surroundings is just everything else. And then a quick preview of the results. The simulated time from the glow script is 1.573 seconds, and the real time I got on average was 1.34 seconds. So let's go over a few important concepts. We have Faraday's law, which gives us our EMF, Biot-Savart law, and then just Newton's laws. These are the kind of things we're going to use throughout. So for the procedure of the experiment, we're essentially just dropping a magnet through the metal tube, and then I'll observe the time it takes for the magnet to fall all the way through the tube. So there are, of course, some initial assumptions with this experiment. One being that air resistance is negligible. This eases the calculations a little bit. Additionally, that the magnet behaves as a perfect dipole, which allows the calculations we're doing to work, at least in that scenario. And then additionally, nothing else in the surroundings having an impact on the system, such as the friction that occurs between the metal tube and the magnet, things of that nature. So here's some of the base data. The magnet's mass, the mu value, length of the tube, width of the tube, etc. And then at the end, the average time, which we already talked about, the 1.34 seconds. So let's take a look at some of the code. We have some initial conditions here on the left, just setting our lengths, our masses, and things like that. A couple of functions for determining the dipole moments and calculating flux, and then just summing up the forces and graphing those so we can actually see what's going on. So here on the left is just a visual representation of the magnet in the tube, and then the main part over here on the right is our graph modeling velocity versus time. And here we can see the computational result we got is that it would take 1.573 seconds to fall all the way through the tube, with a big section in the middle being seen to have a constant velocity, which is something that we'll definitely talk about. All right, here's a few things about interpreting the simulation, those questions. We know that the red is the counterclockwise current and the blue is the clockwise current as seen by Lenz's law. This is the red and blue that can be seen on the glow script model of the magnet actually falling. Additionally, the magnet would fall exactly the same, but the currents would be flipped if we drop the magnet in a different orientation. So speed wouldn't really be affected here. And then if we get to comparing our times between the real magnet fall and the glow script, I got that the real magnet was faster, but this is definitely something we can attribute to errors when taking measurements and even just me dropping it weird or anything like that. Then finally, outside the tube, the gravitational force is greater, but while inside the tube, the magnetic and gravitational forces equal each other. This is why when we saw in the graph that it was going a changing velocity, and then while in the tube, that middle section, our velocity was constant because the forces were canceling each other, netting out to zero. And then outside of the tube, we kept falling again because now gravity is stronger once more. Of course, there are sources of error in this. One could be measurement of objects to an inaccurate degree, it's not precise enough. Timing of the stopwatch, probably not being exact, kind of going with the measurements. And lastly, forces like air resistance and friction of the tube on the magnet, which we already kind of mentioned before. So there's a couple what if questions. One, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, looking at Ohm's law, if we decrease the resistance, then the current induced would have to be even higher, and due to that, we would have a higher induced magnetic field, and our magnet's going to fall even slower than it would otherwise. And then we have, what if holes or slots were cut into the tube? How would this affect the ring current in the model? Well, there would be less rings of current in the entire tube, so ultimately there would be less induced magnetic field, so the magnet is of course going to fall faster because there's less magnetic field to counteract the gravitational force acting on the magnet. And that wraps up Lab 5, and thank you for listening in.